A forgotten history is written across the night sky in faint, ancient light. This starlight is a cosmic time capsule, carrying messages from billions of years before our world existed. We are about to decode the universe's oldest diary, and by the end, your understanding of time and our place in the cosmos will be completely transformed. We will uncover how a single photon can reveal the birth of a galaxy, and how the very atoms in your body were forged inside long-dead stars. What cosmic secret do you hope is waiting to be found in that ancient glow? That faint starlight is more than just a distant glow. It is a ripple in the very fabric of the universe, a messenger carrying a detailed report from a faraway place and time. Every single particle of light, every photon that lands on a telescope sensor, is a tiny envelope of data. The story it carries is written in its unique signature, in its specific color, its precise brightness, and even the direction of its subtle vibration. This vibration, known as polarization, tells us about magnetic fields in the void. The color reveals the scorching temperature of a star's surface, while a slight shift in that color can betray whether a galaxy is racing toward us or fleeing away. This simple, profound idea turns our most powerful observatories into something far greater than cameras. They become time machines, reading the autobiography of the cosmos one photon at a time. And the entire incredible mechanism of cosmic time travel hinges on one fundamental rule of the universe: the finite and unchangeable speed of light. The universe enforces a universal speed limit, one that is absolute and unbreakable. Light travels at an astonishing speed, but it is not instantaneous. This fundamental delay is the engine of cosmic time travel. When you gaze at a star 100 light-years away, the light striking your eye is not a live report. It is a century-old news bulletin carrying an image of that star as it was when your great-grandparents were young. This is not a theoretical concept. It is the daily, practical reality for every astronomer. The deeper we peer into space, the further back into cosmic history we are granted a view. The beautiful, swirling Andromeda Galaxy, our nearest major galactic neighbor, presents itself to us not as it is today, but as it was 2.5 million years in the past, from a time when early humans were just beginning to walk the Earth. This incredible temporal displacement allows scientists to assemble a chronological album of the universe's life. They do not need a single time machine. Instead, they simply look out at different distances, observing infant galaxies, mature stars, and everything in between, all at their respective ages in the past. This foundational principle of looking back in time by looking far away leads us directly to the oldest and most profound photograph ever taken, a glimpse of the universe's very first light. That foundational principle of cosmic time travel leads us directly to the oldest photograph ever taken, a portrait of the universe in its infancy. Rewind the expansion of everything we see to a moment just 380,000 years after the Big Bang. The cosmos was not yet dark and empty. It was an incredibly hot, dense, and opaque fog, a swirling soup of particles and energy where light could not travel freely. It was trapped, constantly bouncing between electrons, but then a pivotal transformation occurred. The universe had expanded and cooled just enough for atoms to form, suddenly clearing the fog. In that instant, the trapped light was set free in a brilliant, universe-wide flash. That primordial burst of energy still washes over us today, a faint microwave whisper from the dawn of time. We call this the cosmic microwave background. It is the very first light, the afterglow of creation itself, this ancient glow is not perfectly uniform. If you could see it with your eyes, it would appear as a nearly even temperature across the entire sky. But sensitive telescopes reveal tiny, ghostly patches, regions that are ever so slightly warmer or colder than their surroundings. These minute temperature differences are the universe's most important imprints. They are the gravitational seeds from which everything we know would eventually grow. Those slightly denser, warmer spots were the cradles for future galaxies, the gravitational anchors that, over billions of years, pulled in enough matter to form the first stars and the vast cosmic web we observe today. By reading this fossilized light, scientists are not just looking at a static picture. They are reading the first chapter of the universe's history book, written in the language of temperature and density. This ultimate origin story sets the stage for the next great cosmic dawn, when the first stars would ignite, ending the universe's dark ages and beginning a new, transformative era. That first cosmic dawn was followed by a long and profound silence, a period often called the Dark Ages. For millions of years, the universe was a vast, featureless expanse of neutral hydrogen gas, a shadowy realm where no new sources of light existed. Then something monumental happened. The first stars ignited. These were not like the stars we see today. Born from the pristine hydrogen and helium of the young cosmos, these first suns, known as population 3 stars, were titans. They were behemoths hundreds of times more massive than our own sun, and they burned with a ferocious, brilliant, and tragically short-lived intensity. Their light was a stark, pure ultraviolet, and it began to perform a fundamental act of cosmic surgery. This intense radiation started to tear apart, or ionize, the neutral hydrogen atoms that filled all of space, stripping them of their electrons and turning the opaque cosmic fog back into a transparent gas. We call this transformative era the epoch of reionization, the moment the universe turned on the lights for good. We have never directly seen one of these first stars. Their individual lives were too brief, ending in spectacular supernova that seeded the universe with the first heavy elements. But we can detect their collective ghostly presence, their impact etched into the light of even more distant objects. When astronomers point their most powerful telescopes at quasars, the intensely bright cores of ancient galaxies, they act as cosmic lighthouses. By analyzing the specific absorption lines in the quasar's spectrum, the unique fingerprints of elements that have absorbed its light along its billion-year journey, scientists can read the history of the intergalactic medium. They can see the telltale signs of neutral hydrogen being systematically burned away, clearing the cosmic fog and creating the transparent universe we inhabit today. The legacy of those first monstrous stars is written into the very fabric of the earliest galaxies we can now observe, their explosive deaths providing the raw materials for all the complex worlds and life that would follow. Those brilliant quasars do more than just mark a distant point in space. They act as the ultimate cosmic flashlights, illuminating the shadowy structures of the early universe. Picture a single, impossibly bright beacon shining from over 12 billion light-years away. As its light begins its epic journey toward Earth, it does not travel through empty space. It passes through a vast, invisible network of gas clouds and filaments, the primordial material that has not yet collapsed into galaxies. This material, mostly hydrogen, is not completely transparent. It acts like a complex cosmic filter, absorbing very specific colors from the quasar's brilliant white light. When astronomers finally capture this ancient beam and spread it out into a rainbow or a spectrum, they do not see a clean, continuous band of color. Instead, they find it scarred with thousands of dark lines, a dense collection of absorption spikes. This pattern is so intricate that scientists call it the Lyman alpha forest, a spectral woodland where every single tree, every dark line, represents a different cloud of hydrogen gas that the light passed through on its way to us. Each line's position reveals the cloud's distance, its width tells us the gas density and temperature, and its subtle shift indicates whether the cloud was moving toward us or away. By reading this forest, astronomers are not just looking at the lighthouse, they are mapping the entire invisible landscape that lies between it and us. They can trace the delicate cosmic web, seeing how matter was distributed when the universe was young and wild. This incredible backlit view provides a direct chemical census of the ancient cosmos, revealing a universe that was once pristine, composed almost entirely of the simplest elements. But that pristine state was about to be permanently and dramatically altered by the very stars whose birth this web of gas made possible. This intricate cosmic filter, the Lyman alpha forest, reveals a universe of startling simplicity. But that simplicity was a prelude to a profound chemical transformation, one we can now read in the light of stars closer to home. Every star carries its own chemical identity card, and we can read it by dissecting its light. When starlight enters a powerful telescope, it is fed into an instrument called a spectrograph, which acts like a hyper-advanced prism. It does not just produce a simple rainbow. It reveals that rainbow to be a precise barcode crossed with a vast number of thin, dark lines. These are not random flaws. Each of these absorption lines is a unique signature, a direct fingerprint of a specific chemical element present in the star's own atmosphere. Imagine every element in the universe has its own secret password, a specific color of light it loves to steal. Hydrogen absorbs one set of colors, iron another, and carbon its own distinct set. By matching these dark lines in a star's spectrum to the known fingerprints of elements we've studied in laboratories, astronomers can perform a remote chemical analysis from thousands of light years away. This is how we know with certainty that our own sun contains not just hydrogen and helium, but also traces of iron, carbon, oxygen, and calcium. This technique, stellar spectroscopy, effectively turns every point of starlight into a cosmic periodic table. But the story goes far beyond a simple ingredient list. The most profound clue lies in what astronomers call metallicity. This is not just the presence of metals like iron, but the overall abundance of any element heavier than helium. Why does this matter? Because the universe began with only the lightest elements. Every single atom of carbon, oxygen, nitrogen, and iron had to be forged later, inside the nuclear furnaces of stars and scattered by their violent deaths. Therefore, a star's metallicity is a direct clock. A star with very low metallicity, one that is almost pure hydrogen and helium, must be ancient. It formed early in cosmic history from gas that had not yet been polluted by generations of previous stars. A star with higher metallicity, like our Sun, is a relative newcomer born from gas enriched by the ashes of countless stellar explosions. By reading these chemical fingerprints, we are not just learning what a star is made of. We are reading its biography and its place in cosmic history, uncovering the life and death of stars that lived and died long before it was even born. That chemical clock we read in starlight is set by the dramatic life and death of the stars themselves. The color and brilliance of a star are not random. They are a direct broadcast of its mass, its age, and its ultimate fate. A brilliant, blue-white star is a cosmic powerhouse, a massive ball of gas burning its fuel with such ferocious intensity that it can shine millions of times brighter than our Sun. But this profligate lifestyle comes at a cost. Such a star lives fast and dies young, exhausting its core fuel in just a few million years before meeting a cataclysmic end. In stark contrast, a dim, cool red dwarf, the most common type of star in our galaxy, is the ultimate miser. It conserves its fuel so efficiently that it can shine steadily for trillions of years, far longer than the current age of the universe. We can organize this entire family of stars on a single, powerful chart called the Hertzsprung-Russell Diagram. This is not just a classification system. It is a stellar family portrait that reveals the precise relationship between a star's color, its true brightness, and its stage of life. The vast majority of stars, including our Sun, fall along a smooth band called the main sequence, where they spend the bulk of their lives steadily fusing hydrogen. But when a star begins to run out of hydrogen fuel in its core, it leaves this main sequence and embarks on its final, often spectacular, acts. A star like our Sun will swell into a red giant, its outer layers gently puffing away into space to form a beautiful, glowing shell of gas called a planetary nebula. For a brief, cosmic moment, this nebula shines with a unique and complex light signature, the ghostly echo of a star's final breath. The exposed core of the star then remains as a white dwarf, a dense, Earth-sized ember that will slowly cool and fade over billions of years. But for stars many times more massive than our Sun, the finale is far more violent. Their cores collapse in a fraction of a second, triggering a supernova explosion so bright it can outshine an entire galaxy. The light from this detonation is unmistakable, a brilliant, transient flash that creates and then flings newly forged heavy elements iron, gold, silver, uranium out across the galaxy. By observing the millions of stars in our own Milky Way, we see every possible stage of this life cycle simultaneously. We witness the hot, young blue stars in stellar nurseries, the steady middle-aged stars like our Sun, and the dying red giants and the remnants of past supernova. It is as if we are watching a single star's entire multi-billion-year life story play out in fast-forward. These stellar deaths are not an end. They are the most crucial act of cosmic renewal, seeding the void with the complex elements that will one day form new stars, rocky planets, and every ingredient necessary for life itself. That brilliant, transient flash of a supernova is far more than a stellar death. It is a cosmic forge operating at unimaginable temperatures and pressures. In the heart of that cataclysm, elements are born that could never form within a star's stable core. The intense neutron flux in the explosion's aftermath slams atomic nuclei together, building heavier and heavier elements in a frantic process lasting mere seconds. This is how the universe creates gold for jewelry, silver for circuitry, and the uranium that powers nuclear reactors. Every precious metal on Earth was once forged in such a violent stellar detonation, then scattered across space like cosmic seeds. This enriched material mixes with interstellar gas, becoming the raw ingredients for new solar systems. The next generation of stars that forms from this cloud will already be richer, more complex, bearing the chemical legacy of those that came before. But the story written in a supernova's light does not end with chemistry. A specific class of these explosions, known as Type Ia supernova, provides one of the most crucial measuring tools in all of cosmology. These occur in binary star systems where a dense white dwarf star steals material from its companion. Once it reaches a very specific, critical mass, it undergoes a runaway thermonuclear explosion. Because this trigger mass is always the same, the resulting explosion always releases nearly the same amount of energy. This makes its peak brightness incredibly consistent. Imagine having a light bulb of known wattage. By measuring how dim it appears from a great distance, you can calculate exactly how far away it is. A Type Ia supernova is that cosmic light bulb. For decades, astronomers used these standard candles to map the universe's expansion. expecting to see the gravitational pull of all matter gradually slowing it down. What they found instead was shocking. The most distant supernovae were fainter than their expected distances predicted. This meant they were even further away than anyone had thought. The only possible explanation was that the expansion of the universe is not slowing down. It is accelerating, propelled by a mysterious, repulsive force we now call dark energy. So the light from a single, dying star tells a dual story. It reveals the violent origin of the very atoms that make up our world, and it acts as a precise ruler that measured the fundamental and utterly surprising geometry of our entire cosmos. Those supernovae give us cosmic mile markers, but what if we wanted to see the entire journey? This ambition led to one of astronomy's most profound experiments. Astronomers pointed the Hubble Space Telescope at a patch of sky that appeared, to every other instrument, completely and utterly empty. It was a dark void, a mere speck, smaller than a grain of sand held at arm's length. For 10 consecutive days, Hubble's gaze remained locked on this single point, collecting every single photon of ancient light that trickled in. The result was not a confirmation of emptiness. It was a revolution. The Hubble Deep Field image revealed a universe teeming with thousands of galaxies, each a faint smudge of light that had been traveling for billions of years to reach us. This was not just a deeper photograph. It was a core sample drilled into the cosmos, a geological stratum of time made visible. Because light takes time to travel, this single image does not show a single moment. It is a galactic family album capturing infant, teenage, and mature galaxies all within the same frame. Their apparent proximity an illusion created by our view across unimaginable distances and into the deep past. The faintest, reddest smudges in that image are the most distant, the building blocks of the universe in its raw, formative years. They are small, irregular, and chaotic, often little more than clusters of young, blue stars blazing in a turbulent swirl of gas. These are the proto-galaxies, the cosmic infants. By comparing them to the more familiar, well-ordered spirals and smooth ellipticals we see in our own cosmic neighborhood, we witness the entire narrative of galactic evolution. We see the mergers, the violent collisions where these small clumps of stars and gas smash together, their gravity tangling and pulling them into new, larger structures over billions of years. The light from these galaxies tells a detailed story even at such vast distances. Their specific color, or redshift, tells us exactly how long their light has been traveling, placing them at a precise moment in cosmic history. The overall shape and brightness reveal their mass and the frantic rate at which they were birthing their first generations of stars. This direct visual evidence shows us that galaxies are not static islands. They are dynamic, living entities that grow, collide, and transform across cosmic time. Every deep field image since, including the breathtaking new views from the James Webb Space Telescope, pushes this frontier further back, closer to the very first galaxies. But to see the grandest structures of all, we must look beyond the galaxies themselves and observe how their immense gravity bends the very fabric of space. The immense gravity of a galaxy cluster does more than just hold stars together. It warps the very space around it, creating a natural cosmic lens. This phenomenon, predicted by Einstein, is called gravitational lensing. A massive object like a cluster acts like a lens in space-time, bending the path of light from galaxies that lie far behind it. This cosmic trick of perspective can stretch a distant galaxy's image into a long, thin arc, or even create multiple mirrored images of the same object arranged in a perfect circle, known as an Einstein ring. This is not an optical illusion. It is a direct confirmation that mass curves space, and light simply follows that curvature. For astronomers, this natural magnifying glass is an invaluable tool. It allows us to see galaxies so distant and faint that they would be completely invisible to our telescopes otherwise. The foreground cluster amplifies their light, giving us a boosted, high-resolution view into the earliest epochs of star formation. But the lensing effect reveals something even more profound. By carefully mapping the precise way the background light is distorted, scientists can create a detailed mass map of the foreground cluster itself. This map includes not just the visible stars and gas, but more importantly, the immense halo of invisible dark matter whose gravity is primarily responsible for the lensing. Gravitational lensing thus lets us see the unseen, tracing the distribution of the cosmos's dominant but mysterious component. This incredible warping of light by mass has a dynamic, rippling counterpart. Just as a lens bends light, the violent acceleration of massive objects sends literal ripples through the fabric of space-time itself. Gravitational waves write a different kind of cosmic history, one felt more than seen. While starlight paints a picture in color and brightness, these waves are ripples in the fabric of space-time itself, a kinesthetic shudder from the most violent events in the universe. They are generated by colossal accelerations, by the final, spiraling dance of two black holes merging into one, or the cataclysmic collision of two ultra-dense neutron stars. This narrative is not carried by photons, but by a literal stretching and squeezing of the cosmos. And unlike light, which can be absorbed, scattered, or bent by dust and gas on its long journey, gravitational waves pass through everything almost completely unaffected. They are a pristine, unaltered signal from the heart of the chaos. We witnessed the profound power of this dual narrative in 2017. For the first time, observatories on Earth felt the distinct tremor of spacetime from a neutron star merger. At nearly the same instant, telescopes across the globe and in space saw a brilliant flash of light from the same patch of sky. A gamma ray burst followed by a rapidly fading glow across every wavelength. This coordinated observation, known as multi-messenger astronomy, was a revolution. It was like being deaf and suddenly gaining the ability to hear the universe's symphony while watching its fireworks display. The data was unequivocal. The specific signature of the light confirmed that the immense pressures and neutron-rich environments in such a collision were indeed cosmic forges, producing staggering amounts of heavy elements like gold, platinum, and uranium. In that single event, we not only heard the spacetime echo of the crash, but also saw the freshly minted elemental debris it ejected. Gravitational waves thus add a dynamic, physical dimension to our cosmic story, revealing processes that are often completely dark to traditional telescopes. They allow us to sense the invisible, to feel the universe rearrange its most massive structures. To capture the full spectrum of these ancient messages, from the faintest photon to the subtlest spacetime ripple, requires an orchestra of increasingly sophisticated tools listening across the cosmos. Capturing the faint whispers of ancient starlight is a monumental feat of engineering. The entire endeavor of modern astronomy is a race to build a better photon bucket. Galileo's first telescope, a simple tube with two lenses, was revolutionary because it gathered more light than the naked eye alone. That core principle has driven every leap forward since. A telescope's mirror is its light bucket. The larger its surface area, the more of those precious, ancient photons it can catch from a single, faint object in the deep void. Doubling the diameter of a mirror does not just double its light-gathering power, it increases it by a factor of 4, allowing us to see objects 16 times fainter. This is why we build behemoths, like the extremely large telescope under construction in Chile, with a mirror spanning 39 meters. It is designed to directly image planets orbiting other stars and to peer into the earliest epochs of galaxy formation. But size is only part of the challenge. Our own planet's atmosphere acts like a shimmering, turbulent veil. It blurs the pinpoint light of stars, the very effect that causes them to twinkle, and it blocks entire bands of radiation, like much of the infrared spectrum. This is why we launch observatories into the vacuum of space. The Hubble Space Telescope, orbiting high above this atmospheric distortion, provided our first crystal-clear views of the deep universe. Its successor, the James Webb Space Telescope, was specifically engineered for the infrared. The most distant galaxies, whose light has been stretched into longer, redder wavelengths by the expansion of the universe, shine brightest in this invisible light. Webb is not just a bigger eye. It is an eye designed to see a specific, ancient color that has been hidden from us until now. For telescopes that must remain on the ground, a brilliant solution has emerged. Adaptive optics systems fire powerful laser beams into the upper atmosphere to create an artificial guide star. Sensors then measure the distortion of this fake star in real time, and a computer commands a deformable mirror to flex and contort hundreds of times per second, canceling out the atmosphere's blur. The result is a view from the Earth's surface that can rival the clarity of Hubble. These technological marvels, from vast mirrors to intelligent optics, are our direct conduits to the cosmic past. They collect the universe's oldest stories, allowing us to read them in exquisite detail. And with this sharpened vision, we have begun to investigate the cosmos' most mysterious component, an invisible presence whose gravity sculpts everything we see. The universe is built upon an invisible architecture. We know this not because we can see this hidden framework, but because we can watch its immense gravity manipulate the light that passes by. Dark matter, a substance that does not emit, absorb, or reflect a single photon, reveals its presence by the shadow it casts upon the cosmos. Its story is told entirely through its gravitational handiwork. One of the most compelling pieces of evidence comes from watching how stars move within their galactic homes. Imagine our own Milky Way. All the stars, including our Sun, are orbiting the galaxy's center. According to the laws of gravity, stars farther from the center, where the visible mass is more spread out, should move more slowly, just as Pluto orbits our Sun much more sluggishly than Mercury. But this is not what we observe. Stars in the outer reaches of spiral galaxies orbit at nearly the same high speed as those closer in. The only way this makes sense is if every galaxy is embedded within an enormous, massive halo of something we cannot see, a spherical cloud of dark matter whose gravity grips the stars, whipping them around at these unexpected velocities. The visible galaxy is just the bright, dense core at the heart of a much larger, invisible beast. This gravitational influence extends far beyond a single galaxy's borders. We see it on the grandest of scales through the phenomenon of gravitational lensing. When light from a tremendously distant galaxy travels toward us, its path is subtly bent as it passes through the gravitational field of a massive foreground cluster. By meticulously mapping the resulting distortions, the way background galaxies are stretched into faint arcs and smears, astronomers can perform a kind of cosmic cartography. They can draw a detailed mass map of what is actually there, and the result is astonishing. The map shows that the vast majority of the cluster's mass, the mass doing the lensing, does not align with the glowing patches of galaxies. It forms a smooth, massive scaffold, a skeleton of dark matter upon which the visible universe is draped. Every flash of starlight, every distorted galaxy we observe, is therefore carrying two messages. One is its own story of birth and evolution. The other is a coded report on the unseen dark matter it had to travel through to reach our eyes. This invisible substrate does not just hold galaxies together, It governs the overall expansion of the cosmos, a final, profound secret written into the ancient light from the dawn of time. Edwin Hubble's discovery forever changed our cosmic address. He found that the light from distant galaxies is not just old, it is stretched. The color of that ancient starlight systematically shifts toward the red, as if the very waves are tired from their long journey across an expanding cosmos. This redshift is not random. The farther away a galaxy is, the greater its light is stretched, meaning the universe itself is stretching, carrying galaxies away from each other like raisins in a rising loaf of bread. The rate of this expansion is a single, crucial number known as the Hubble constant. It is the speedometer for the entire universe, telling us how fast space is stretching for every million light-years of distance. Pinpointing this number has become one of the most important quests in modern science. Astronomers use cosmic lighthouses, like the rhythmic pulsations of Cepheid variable stars and the uniform brilliance of Type Ia supernova, to build a cosmic distance ladder, carefully measuring how fast each rung is moving away. But a puzzling conflict has emerged. Measurements of the early universe, taken from the pristine snapshot of the cosmic microwave background, give one value for the Hubble constant. Meanwhile, measurements from the modern, local universe using supernova and other markers give a slightly different, faster value. This discrepancy is known as the Hubble tension. It is a small but persistent gap that suggests our understanding of cosmic history may be incomplete. Perhaps dark energy, the mysterious force driving the acceleration, is not constant but changing over time. Or maybe there is an entirely new type of particle or field influencing the expansion. The simple redness of a galaxy's light, a basic observation, has become the front line in a search for new physics. It tells us the universe is not just expanding, but that its expansion holds a deeper story, one intimately woven with the other great cosmic mystery, the nature of dark energy itself. That accelerating expansion is the universe's most profound and unsettling secret. For decades, the logical assumption was that the mutual gravitational pull of all matter, of every galaxy and star and cloud of dust, would be relentlessly slowing the cosmic expansion, applying a universal brake. The great question was whether there was enough matter to eventually pull everything back together in a big crunch, or if the universe would just coast onward forever, gradually slowing. Then, in the late 1990s, two independent teams using Type Ia supernova as cosmic mile markers made a discovery that overturned everything. They found that the most distant stellar explosions, the ones whose light had been traveling for billions of years, were significantly fainter than their predicted distances demanded. The only possible explanation was that these supernovae were even farther away than anyone had calculated. The expansion of space itself had not been slowing down. It had been speeding up. A mysterious, repulsive force was stretching the cosmos apart at an ever-increasing rate. We call this force dark energy. It is not a minor component. Current measurements indicate that dark energy constitutes about 68% of the entire energy budget of the universe. It is the dominant force shaping cosmic evolution, and yet we have no idea what it actually is. The most straightforward candidate is the energy inherent to the vacuum of space itself, a concept Einstein once proposed and then discarded as his greatest blunder. If this vacuum energy is real and constant, it paints a specific, chilling portrait of our ultimate fate. In this scenario, the acceleration continues unchecked. Billions of years from now, the expansion becomes so rapid that it overwhelms all other forces. Galaxies outside our local group would be pushed away, their light stretched beyond the visible spectrum until they vanish from the sky entirely. Eventually, the space between individual stars within our own galaxy would begin to stretch, and later, the very fabric of solar systems and atoms would be torn asunder in a final, catastrophic event known as the Big Rip. The dimming of a few ancient supernovae thus opened a window onto the cosmos's final chapter, but the story of that light does not end when it leaves a star. Its journey to our telescopes is an epic voyage through a dusty, complex interstellar medium, and the dust itself has a tale to tell. That cosmic dust is far more than a simple obstruction. Drifting in the vast spaces between stars, these microscopic grains of silicate rock and carbon soot form a diffuse, hauntingly beautiful mist. Their effect on starlight is a constant, gentle filter, scattering shorter, bluer wavelengths of light and allowing the longer, redder ones to pass through. This process, called interstellar reddening, is precisely why our sunsets glow with such rich, crimson hues, and it explains why distant stars often appear redder and dimmer than they truly are. This dust can be a frustrating veil, hiding the brilliant cores of galaxies and the birthplaces of stars from our optical telescopes. Yet, in this seeming obstruction lies a deeper purpose. These tiny grains are fundamental cosmic architects. Their solid surfaces provide a rare meeting place in the vacuum of space, a platform where simple atoms like hydrogen, oxygen, and carbon can stick, meet, and slowly assemble into increasingly complex molecules, including the prebiotic building blocks of life itself. The dust motes become microscopic laboratories, brewing the chemistry for future worlds, and when these dust grains are warmed by the heat of nearby stars, they do not glow in visible light. Instead, they radiate a gentle, thermal warmth in the infrared part of the spectrum. This is where our view transforms. Telescopes like the James Webb Space Telescope are specifically designed to see this infrared glow. The very dust that blocks our optical view becomes a brilliant, illuminating canvas in infrared light. Suddenly, the dense, dark clouds that appear as mere shadows in visible light reveal themselves as vibrant, intricate stellar nurseries. We can peer directly into the swirling cocoons of gas and dust where new stars and their planetary systems are actively coalescing. So this dust is both a curtain and a revealer. It obscures one chapter of the cosmic story while simultaneously recording the next, its infrared signature writing the first pages in the biography of unborn solar systems. These swirling disks of cosmic dust and gas are the birthplaces of worlds. Around a young star, a vast, flat disk of primordial material begins to organize itself, a whirlpool of potential governed by gravity and momentum. This is a protoplanetary disk, the raw blueprint for an entire solar system. With revolutionary instruments like the Atacama Large Millimeter Submillimeter Array, or ALMA, we are no longer just theorizing about this process. We are watching it unfold in breathtaking resolution. ALMA network of radio telescopes acts as a single, colossal eye, tuned to see the faint glow of cold dust and gas in the far reaches of these disks. The images it returns are not featureless smudges. They are intricate celestial fingerprints, etched with dark gaps, bright rings, and elegant spiral arms. Each of these structures is a direct, visible clue. A clean, dark gap circling the star is not an empty void. It is the gravitational wake of an infant planet, a cosmic snowplow clearing its orbital path as it grows. A bright, dense ring of material might mark a pressure trap, a region where dust grains are piling up, colliding, and sticking together to form the very building blocks of planets, from tiny pebbles to massive planetary cores. But the story goes far deeper than just shapes. The specific wavelengths of light emanating from these disks carry a chemical barcode. By analyzing this light, astronomers can perform a remote inventory of the disk's composition. They can identify the spectral signatures of water ice frozen onto dust grains, of complex organic molecules like methanol and even simple sugars, and of various silicate minerals that will one day form the rocks of terrestrial planets. This is how we read the ingredient list for new worlds. We can see that the materials for oceans, for atmospheres, and for the chemistry of life are present from the very beginning, woven into the fabric of these stellar nurseries. By studying these cosmic construction sites, we are effectively looking back at the early history of our own solar system, understanding how a chaotic cloud of gas and dust around a newborn sun transformed into the orderly family of planets, asteroids, and comets we call home. This discovery brings our journey through cosmic history full circle, connecting the explosive deaths of the first stars that seeded the universe with heavy elements to the serene formation of new planetary systems that may one day cradle life. This cosmic fine-tuning is written into the universe's oldest light. Every physical constant, every fundamental force, appears to be set with an almost impossible precision, a delicate balance that made our existence possible. We call this profound observation the Anthropic Principle. It is the simple yet staggering idea that the universe we are capable of observing must be compatible with the existence of observers. The data supporting this is not philosophical speculation. It is etched into the faint temperature variations of the cosmic microwave background. If the initial density of the universe after the Big Bang had been even marginally higher, gravity would have pulled all matter back into a catastrophic collapse long before stars could ever form. If that density had been slightly lower, the cosmic expansion would have been so rapid that matter would have flown apart, never coalescing into the first galaxies. The strength of gravity, the force that builds stars and planets, is itself a razor's edge. A tiny bit stronger, and stars would burn through their fuel in millions of years, far too quickly for life to evolve on any orbiting world. A fraction weaker, and the nuclear furnaces in stellar cores would never ignite, leaving the universe dark and lifeless. This fine-tuning extends to every fundamental interaction, from the nuclear forces that build atoms to the cosmological constant driving the universe's acceleration. The light we have decoded reveals a cosmos that is not just any random universe, but one specifically tailored, through its laws and its history, to eventually give rise to beings who can look back and wonder at it. Our very act of observation connects us to this chain of cosmic causality, placing humanity within a vast billion-year timeline that had to unfold exactly as it did for us to be here. This profound perspective, born from the hard data carried by ancient photons, is now being tested and refined by a new generation of space missions, each one designed to read the universe's first light with even greater clarity, searching for the subtle clues that explain why our cosmic home is so perfectly suited for life. These future observatories are not merely upgrades, they are entirely new senses for the cosmos. The Nancy Grace Roman Space Telescope, slated for launch later this decade, will function as a panoramic wide-angle lens on the universe. Its field of view will be 100 times larger than that of the Hubble Space Telescope, enabling it to map the cosmos with a speed and scope previously unimaginable. This vast survey will capture the light from billions of galaxies, tracing the subtle imprint of dark energy on the large-scale structure of the universe across cosmic time. It will also perform a detailed census of thousands of distant exoplanets through gravitational microlensing, a technique where a star's gravity briefly magnifies the light of a background star, revealing the presence of otherwise invisible orbiting worlds. While Roman surveys the sky, another mission will be listening for a different kind of signal. The Laser Interferometer Space Antenna, or LISA, will be the first gravitational wave observatory in space. It will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by laser beams. This colossal instrument will be tuned to the low-frequency rumble of the universe, detecting the space-time ripples from events that are utterly silent to our current detectors. It will hear the final, spiraling dance of supermassive black holes at the hearts of merging galaxies, a deep bass note from the most powerful collisions since the Big Bang. This will open an entirely new window onto how the largest structures in the cosmos came to be. Back on the ground, a behemoth is taking shape. The extremely large telescope is being built atop a mountain in Chile, its primary mirror an immense 39 meters across. Its sheer light-gathering power, combined with advanced adaptive optics, will allow it to perform a feat that once seemed like pure science fiction. It will attempt to directly image the atmospheres of rocky, Earth-sized exoplanets orbiting nearby stars. By analyzing the starlight filtering through those alien skies, scientists will search for the chemical fingerprints of water, vapor, methane, oxygen, and other potential biosignatures. These missions form a coordinated assault on the frontiers of knowledge. Together, they will push our view back to the very dawn of the first stars and galaxies, rendering the cosmic web in sharper detail than ever before. Each new observatory represents a deeper, more nuanced question in our ongoing dialogue with the universe, a conversation conducted entirely by interpreting the ancient messages carried to us across the void. The answers we find will undoubtedly be profound, but they will also be fleeting, instantly replaced by new and even more bewildering mysteries. This brilliant interplay of light and shadow has revealed a cosmos of breathtaking structure, yet its deepest foundations remain shrouded in mystery. We have mapped the grand narrative of the universe, but the plot is driven by characters we cannot see and forces we do not fully understand. The true nature of dark matter is a ghost in the cosmic machine. We feel its gravitational grip, we map its invisible scaffolding, but we have no idea what it is made of. Is it a sea of undiscovered particles, a trillion times lighter than an electron, streaming through our bodies every second without a trace? Or could it be something even more exotic, a relic from the universe's first moments that challenges our very understanding of physics? And then there is dark energy, the engine of cosmic acceleration. Is it truly the constant energy of empty space, or is it a dynamic field that has changed over the lifespan of the cosmos, perhaps even growing stronger? The answers to these questions will dictate the ultimate fate of everything, from the vastest galaxy to the atoms that make us. They are written into the ancient light, but we have not yet learned how to read that part of the message. Even our origin story holds a pivotal blank space. What was the trigger for cosmic inflation, that stupendous burst of growth that launched the universe from a quantum speck to a macroscopic reality in a fraction of a second? The light from the cosmic microwave background gives us a baby picture from just after this event, but the moment of inflation itself remains hidden behind an impenetrable curtain. We see its consequences everywhere in the overall smoothness and geometry of the universe, but its cause is one of cosmology's greatest unsolved puzzles. And on a more intimate scale, the question of life persists. We now know that planets are common, and that the essential chemical ingredients for biology are scattered throughout interstellar space and woven into newborn solar systems. But is the universe teeming with life, or is Earth a solitary oasis? The light from a distant exoplanet's atmosphere may one day carry the spectral signature of oxygen and methane, a potential biosignature that would revolutionize our place in the cosmos. These are not gaps in our knowledge so much as they are new frontiers. The recent observations from the James Webb Space Telescope perfectly illustrate this. The telescope saw galaxies in the very early universe that were far too massive and too structured to exist under our current models. Their unexpected brightness is not a refutation of science, it is a clue. It is the universe telling us our story is incomplete, that galaxy formation in the primordial cosmos was somehow faster and more efficient than we ever dreamed. Every mystery is an invitation. Each time we answer a fundamental question, we do not reach an end. We simply peel back a layer of reality to find a deeper, more complex, and more wondrous puzzle waiting beneath. This relentless pursuit, driven by the faint whispers of ancient starlight, is a fundamental human endeavor to understand our home and our story within it. This impulse to map the heavens is written in our oldest stories. Long before we had telescopes, people gathered around fires and looked up, tracing imaginary lines between the stars. They saw heroes, beasts, and gods in the constellations, crafting myths to explain the cosmos and their place within it. These stories were our first cosmological models, born from the same deep-seated wonder that drives an astrophysicist today. The questions we ask are now framed in the language of mathematics and physics, not mythology, but the essential yearning is identical. We are still trying to understand where we came from and what it all means. Every spectrum taken from a distant quasar, every pixel in a Hubble Deep Field image, is part of that continuous human conversation with the sky. It is a collective project spanning generations, a testament to our ingenuity and perseverance in the face of the immense unknown. This intellectual journey from myth to measurement is powered by an unbroken chain of curiosity. It connects the storyteller gazing at Orion to the engineer aligning a laser guide star, all united by a single drive to pull back the veil and see what lies beyond. Our modern tools are simply the latest way to satisfy an ancient, fundamental need to find our story written in the stars. Our natural vision is limited to a single, narrow band of rainbow colors, a tiny window onto the cosmos. Yet the universe communicates its entire history across a vast electromagnetic spectrum, from long, gentle radio waves to the blistering spikes of gamma radiation. Think of visible light as one note in a grand cosmic symphony, while telescopes that see in other wavelengths allow us to hear the full orchestra. Each type of light reveals a different chapter of the story, uncovering phenomena our eyes alone could never perceive. Radio telescopes, with their vast, dish-shaped antennas, tune into the universe's faintest whispers. They detect the cold, dark clouds of molecular gas where future stars are born, and they capture the most important static of all, the faint afterglow of the Big Bang itself, the cosmic microwave background. When we shift our view to the infrared, we can suddenly see through the obscuring cosmic dust that blocks visible light. What was once a dark, impenetrable nebula becomes a transparent stellar nursery, glowing with the warmth of infant suns and the swirling disks that will one day become planets. Ultraviolet light, emitted by the hottest, most massive stars, acts as a brilliant highlighter pen in the cosmic text, tracing out the violent regions of recent star birth and the energetic halos of hot gas that surround galaxies. At even higher energies, the X-ray view unveils the most extreme environments in the universe. The superheated million-degree gas swirling into a black hole's accretion disk, or the remnants of a supernova explosion, all blaze in X-ray light, revealing the locations of immense gravitational and magnetic violence. Finally, at the top of the energy scale, gamma-ray telescopes witness the universe's most catastrophic explosions. The mergers of neutron stars and the deaths of colossal stars announce themselves with brief, unimaginably powerful bursts of gamma radiation, the most energetic photons in existence. By building instruments sensitive to all these wavelengths, we have not just built better telescopes, we have given ourselves new senses. A multi-wavelength observation of a single galaxy is like seeing a city for the first time with night vision, thermal sensors and radar all at once. The visible light shows you the streetlights, the infrared reveals the warm people inside buildings, the X-rays show you the power plants, and the radio waves map out all the roads and communication networks. Only by combining every band of light can we read the universe's complete autobiography, a story written in invisible ink and revealed only to those who know how to look. The vast river of data flowing from our telescopes is more than any single team of scientists can possibly process. This incredible volume of cosmic information has given rise to a powerful new force in astronomy, the global community of citizen scientists. Online platforms like Galaxies present volunteers with real images of distant galaxies, asking a simple but profound question: what shape do you see? The human brain's innate talent for pattern recognition, for spotting the subtle difference between a majestic spiral and a smooth elliptical galaxy, consistently outperforms even the most advanced computer algorithms. With millions of galaxies to classify, every pair of eyes makes a genuine difference, turning a casual observer into an active participant in cosmic cartography. This is not busy work. Participants in these projects have made legitimate discoveries, stumbling upon entirely new classes of objects, like the whimsically named green pea galaxies, which are small, dense, and undergoing furious bouts of star formation. Beyond the digital realm, amateur astronomers with their own backyard telescopes contribute a different kind of vital data. They perform the long-term, patient monitoring of variable stars, whose rhythmic brightening and dimming provides crucial distance measurements across the galaxy. It is often an amateur, diligently comparing the night sky to star charts, who is the first to spot the telltale new point of light that signals a supernova in a distant galaxy or the faint, fuzzy glow of a newfound comet. This collaborative effort does more than just accelerate research. It fundamentally democratizes the process of discovery, proving that the analysis of ancient starlight is not the exclusive domain of a select few with advanced degrees. It is a human heritage, a story that anyone with curiosity and an internet connection can help to write. This collective endeavor allows us to build a more complete and nuanced picture of the universe, a grand project that naturally includes a deeper understanding of our own local galactic neighborhood, the magnificent spiral we call home. Our own galaxy holds a secret history, one we are only now learning to read. The Milky Way is not a static island of stars but a dynamic, evolving entity with a biography written across its vast expanse. We have become galactic archaeologists, using the light from its billions of suns to excavate this past. The European Space Agency's Gaia mission is our premier tool for this dig, providing exquisitely precise measurements of the positions, motions, and brightness of nearly 2 billion stars. This flood of data lets us trace the ancestry of our cosmic neighborhood. We can now identify faint rivers of stars flowing in graceful arcs through the galactic halo. These are stellar streams, the ghostly remains of smaller dwarf galaxies that ventured too close to the Milky Way's immense gravitational pull. Over billions of years, our galaxy has cannibalized these neighbors, tearing them apart and weaving their stars into its own fabric. The chemical composition of a star acts as a time capsule, revealing its origin and age. The ancient stars that populate the galactic halo, the sparse spherical cloud surrounding the main disk, are metal poor. They are made of almost pure hydrogen and helium, indicating they formed in the early universe from pristine gas, before countless supernovae had a chance to enrich the cosmos. In stark contrast, the stars in the bright, flat disk of the Milky Way, including our own sun, are metal-rich. They were born much later from gas clouds that had been repeatedly seeded with the heavy elements forged inside previous generations of stars. This chemical dichotomy tells a clear story of two distinct epochs of formation. The halo represents the galaxy's chaotic, violent infancy, built from the initial collapse of gas and the debris of early mergers. The orderly disk formed later as the remaining gas settled into a spinning plane, giving birth to newer, more chemically complex stars like our Sun. By connecting a star's motion to its chemical fingerprint, we can rewind the galactic clock. We can watch as stellar streams from past mergers settle into the halo and see how the disk gradually built itself over time. The Milky Way's history is a story of cosmic digestion, a relentless process of growth through consumption that mirrors the evolution of galaxies across the entire universe. There is a final, absolute boundary to our cosmic vision, a horizon beyond which no telescope can ever see. This limit is not a flaw in our technology, but a fundamental consequence of the universe's finite age and the unwavering speed of light. We can peer back to the glow of the cosmic microwave background, but we cannot see a single moment before it. The era before that first light is a permanent blind spot, a time when the universe was so dense and hot that light was trapped, rendering it completely opaque. This cosmic horizon definitively answers a centuries-old puzzle known as Olber's paradox. If the universe were truly infinite, static, and filled with an endless number of stars, then every single line of sight in the night sky should eventually land on the surface of a star. The entire heavens should be as brilliantly, uniformly bright as the surface of the sun. Yet our nights are profoundly dark. The resolution lies in the dynamic nature of our cosmos. The universe is not infinite in age. It is only 13.8 billion years old. The light from stars beyond a certain distance simply has not had enough time to reach us. Furthermore, the relentless expansion of space stretches the light from the most ancient, distant sources, redshifting their visible energy into the faint, invisible whisper of infrared and radio waves. This means our entire observable universe, with its hundreds of billions of galaxies, is just a finite bubble of visibility, one historical record among a potentially infinite number of unobservable realms. We are forever tethered to this island of light, a library whose oldest books are written in the fading ink of redshifted photons. Yet, this very limitation forces a profound shift in our search for answers, pushing us to listen for the echoes of the unseen in the fabric of spacetime itself. There is a fundamental limit to how far back our telescopes can see, yet our curiosity does not stop at that barrier of primordial light. Where direct observation ends, the power of theoretical cosmology begins, building entire histories from the language of mathematics. These are not mere guesses, but rigorous simulations that model the universe's evolution from a fraction of a second after the Big Bang all the way to the present cosmic web we observe. The equations act as a time machine governed by our best understanding of gravity, particle physics, and the strange rules of quantum mechanics. They ingest the clues we have gathered from starlight and the cosmic microwave background, and they project the narrative backward into the unseen and forward into the distant future. A perfect example is the theory of cosmic inflation, the near-perfect uniformity of the cosmos, a key feature etched into the CMB, was a profound puzzle. How could regions of space too far apart to have ever been in contact display such identical temperatures? Inflation proposes a breathtaking solution, a period of faster-than-light expansion in the universe's very first moments, stretching a microscopic patch of space into a macroscopic cosmos and ironing out all its wrinkles. This theoretical idea was developed to explain an observational clue, and it went on to make other predictions about the pattern of the CMB's tiny fluctuations, predictions that were later spectacularly confirmed. This is the beautiful feedback loop of cosmology. Observation provides the anchor points, the fixed data in the cosmic timeline. Theory then weaves a narrative that connects these points, a narrative that must be logically consistent and make new, testable predictions. When a new telescope like the James Webb sees something unexpected, like impossibly early massive galaxies, it is not a failure of science. It is a new data point, a challenge thrown down to the theorists, forcing them to refine their models of dark matter, galaxy formation, or the very nature of the first stars. This collaborative dance between the seen and the unseen allows us to reconstruct a coherent history from scattered clues. By running these sophisticated cosmic simulations forward, we can even predict the ultimate fate of the celestial archive we have been decoding. Will the accelerating expansion eventually tear the fabric of spacetime, rendering all future cosmic history forever unreadable? The equations suggest that the light reaching us in the far future will tell a vastly different and lonelier story. Our current window into the cosmic past is a temporary privilege, one that will not last forever. The relentless acceleration of the universe's expansion is actively erasing the deepest chapters of our history book. Each distant galaxy we now observe is not just moving away, its light is being stretched into longer and longer wavelengths. Over billions of years, this stretching will pull their light completely out of the visible spectrum, through the infrared, and eventually into the undetectable realm of radio waves. They will not simply fade, they will vanish from our view entirely as they cross an invisible boundary called the cosmic horizon, receding faster than their light can ever hope to reach us. The brilliant tapestry of the external universe will go dark. The afterglow of the Big Bang itself, the cosmic microwave background, will cool and dilute into a whisper so faint it will become indistinguishable from the empty background of space. For any civilization that awakens in the far future, perhaps tens of billions of years from now, the night sky will tell a profoundly different story. Their cosmos will consist of a single, colossal elliptical galaxy, the merged remnant of our own Milky Way and the approaching Andromeda, set against an otherwise eternal and featureless blackness. They will have no evidence of a universe in expansion, no clue that everything began in a fiery Big Bang. The key discoveries that define our modern cosmology will be permanently inaccessible to them. This realization places our present era in a staggeringly unique position. We exist in a golden age of cosmic archaeology, a brief sliver of time where the critical evidence for the universe's origin, evolution, and ultimate fate is still within our observational grasp. We are the first generation in history to possess both the technology and the accessible data to read this story. This is not just a fortunate accident of timing. It is a profound responsibility. We are the universe's temporary archivists, tasked with decoding and preserving its history before the final pages fade forever into the silent, expanding dark. This cosmic story is not just a collection of facts. It is a precious inheritance, one that comes with a profound responsibility. Decoding the universe's oldest diary fundamentally changes our perspective. It replaces a sense of human centrality with a deep cosmic humility. We learn that we are not merely placed in the universe, but that we are a product of its long and intricate history. Every element in our bodies, every molecule of air we breathe, was forged in the heart of a star that lived and died long before our sun was born. This shared stellar origin story erases arbitrary boundaries, reminding us that all life on Earth is built from the same ancient, recycled stardust. This realization can and should inspire us to become better stewards of our fragile, pale blue dot. In the incomprehensible vastness of space and time, this planet is the only home we have ever known. Its atmosphere, its oceans, and its delicate biosphere are not just a happy accident. They are the direct result of that billion-year-long cosmic process, the final, temporary repository of all those ancient stellar elements. To harm this world is to thoughtlessly discard the rarest of cosmic gifts. As the only species we know of that can comprehend this grand history, we have a unique duty. We must preserve this hard-won knowledge against the slow fade of cosmic forgetfulness. We must continue the quest for understanding, pushing the boundaries of our telescopes and our minds. And most importantly, we must pass this epic story on to future generations, ensuring the flame of cosmic curiosity continues to burn. We are not passive observers of the cosmos. We are a conscious part of its ongoing story, made from stardust and now gifted with the ability to look back and read our own origin myth. From the faint afterglow of the Big Bang to the specific spectral lines of a dying star, ancient Starlight is an immutable record, the only permanent archive of our cosmic past. It is a messenger, a time machine, and a chemical fingerprint all at once, preserving a history that would otherwise be lost to the void. This light allows us to reconstruct an epic narrative stretching from the universe's first fiery moments to the serene formation of planets capable of nurturing life. This profound knowledge does more than just inform us. It connects us directly to the cosmos in the most intimate way possible, revealing that the iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the heart of a long-vanished star. We are quite literally made of star stuff. The quest to read this celestial archive, to decode the universe's oldest diary, stands as one of humanity's most magnificent achievements. It is a story written in light, waiting for anyone with the curiosity to look up and see it. The next time you stand under a dark sky, remember you are not just looking at distant points of light. You are gazing into a deep, historical past, witnessing a chronicle billions of years in the making. What part of this cosmic story resonates most deeply with you? Share your thoughts in the comments and subscribe to continue this incredible journey of discovery together.